So you've already completed the flash activity from the University of Wisconsin, gone through that presentation. I hope you actually solved those problems and took some time to do it and watched the previous video. I'm just going to go back over some of the same concepts in a different way, just to give you another way to look at it. Alright, so let's talk about gears. Gears, pulleys, and sprockets are all mechanisms used to transfer energy by rotational motion or rotary motion. Alright, so we can use these kinds of systems to change the speed of rotation, the direction of rotation, and to change the amount of torque available to do work. Alright, so I want to be sure that you understand the difference between a gear and a sprocket. A gear is mated with another gear. A sprocket has a chain on it to be mated to another sprocket. Alright, so gears go with gears, sprockets go with chain and other sprockets. Alright, so a gear train is a mechanism we use to transmit or move rotary motion and torque through interlocking teeth. Alright, a gear train is made anytime we put two or more gears together. And we say the driver causes the motion and the driven has the motion transferred to it. Alright, so two gears that mate always turn in opposite directions. You'd use a gear in the middle called an idler gear, right, to allow the driver and the driven to rotate in the same direction. So if you'll look here on the top of the page, alright, you can see that the blue gear, okay, is moving clockwise. So the red gear is moving counterclockwise. Alright, and so it will go clockwise, counterclockwise, back and forth through a gear train. Alright, if you look at this one on the bottom, alright, you can see that the first blue gear is the driver and it's rotating clockwise. Then there's an idler gear in the middle, alright, and that idler gear turns counterclockwise. Then the third gear turns clockwise as well. Okay, if you're going to make gears together, they always have the same size teeth, or we say they have the same diametric pitch. Usually instead of teeth we just say pitch. They have the same size teeth, we say they have the same pitch on the teeth. Alright, in this one you can see that there are three gears. Two of them are on the same shaft. Alright, the RPM's revolutions per minute of the large gear is always slower than the RPM of the small gear. Right? The two gears on that same shaft, the yellowish green and the blue, they're always going to turn in the same direction and at the same RPMs. Right? So both that yellow gear and the blue gear are turning clockwise because they're mounted on the same shaft and they have the same speed. Right? Okay, so gear ratios have a number of variables, and they are the number of teeth, the diameter, the angular velocity or the speed, alright, and that funny looking W is the Greek symbol omega. A lot of times in the interest of speed you'll see me just write that as W or RPM, and T is torque. Okay, so those things all have to be in a specific ratio. Alright, they're always related by the same ratio. Alright, so if the number of teeth on the input gear, in is the driver, out is the driven. Okay, so here you can see the number of input teeth is 6. On the output gear, alright, it's 12. Look in the picture here. Alright, we're saying that this red one is the driver, blue is then the driven. Right, and look how the rotations are in opposite directions. Right, the diameter is 2 inches for the input and 4 inches for the output. the rotational velocity, okay? For the input, it's 40 RPM, all right? For the output, it is 20 RPM, all right? So as I went from a small gear to a large gear, I got a decrease in the rotational speed, all right? I got a decrease in speed. That means that, just like we talked about in some of the other simple machines, you don't get something for nothing, to quote one of my other students. You don't lose that speed and get nothing out of it. What you get out of it is an increase in torque, all right? So small to large is going to give you an overall decrease in speed, but an increase in torque. And you can see the input torque is 40 foot-pound, the output torque is 80 foot-pound. All right, so gear ratios, all right? GR, I'm using to be the gear ratio here. The gear ratio is the mechanical advantage of a gear train, okay? And look, I wrote GR over 1, but that was just to kind of help you do the cross, multiply, and divide, all right? So let's go through what that looks like. So all of these things, the output number of teeth over the input, the output diameter over the input. Look, speed's upside down, guys. The input velocity over the output velocity, and the torque output over the torque input, all right, are all in the ratio of 2 to 1. Please notice that velocity is input over output. Everything else is output over input. All right, all of that's in the ratio of 2 to 1. Okay, so let's look at this one. What's the gear ratio between gear A and B? All right, so the gear ratio is the output over the input. So A is going to be our driver for our system. All right, and so the first, it's going to be our driver, it's our input. Okay, then B is going to be the first output. So it'll be 12 divided by 20. All right, and so that works out to be 0.6. All right, now if I do the ratio between B and C, because if I just look at them, all right, then what happens is B is the input and C is the output, right? So that would be 12 over 5. Okay, and then the ratio between C and D. Now C is the input and D is the output, so it'll be 5 over 20. Sorry, I said that backwards, 20 over 5. Excuse me. All right. So what's the total gear ratio of that train? We multiply the individual gear ratios together. We do 0.6 times 0.42 times 4 over 1. And that works out to be 1 over 1. Okay, I don't want you to miss this, guys, that the gears in the middle, okay, because these are all on different shafts. None of these are stacked on the same shaft. Remember that this was the output and the next time it was the input. So it cancels each other out. The next time then, first it was an output, then it was an input. If I multiplied all those together, it actually cancels the next one out. All right? So the total gear ratio for this gear train is basically the ratio between the output and the input gear. All right? So if they were connected directly to each other, the gear ratio would be 1. All right, so what would the total gear ratio be if the last gear had 40 teeth? It would be output was 40 divided by the input 20. That works out to be a ratio of 2 to 1. All right, so when they're all on different shafts, you can do it that way. You don't have to go through all the intermediate steps. Please notice that is only when they are all on different shafts. Okay, let's also go over rotation. If the first one here, okay, is going counterclockwise, this one will go clockwise. Then this one will go counterclockwise. Then this one will go clockwise. Alright, so it goes every other one, it changes. Alright, let's look at a compound gear train. Alright, so this green gear is going to be my driver, and I put the white dots there so you can see them rotating. Alright, and then we put it connected to a yellow gear. Alright, now you can see that as I went from the green to the yellow gear, I got a decrease in speed, which means I got an increase in torque, right? Right now on a compound gear train, some of the gears are going to be on the same shaft. So now I've put the blue on the same shaft as the yellow. So is it moving at the same velocity, rotational speed as the yellow? Yes. Okay, you see that the two white dots there on the yellow and the blue, they stay in the same relation to each other. So finally I mate the blue gear with the red gear. Alright, and so in that scenario, okay, now you can see that the red gear is much larger than the blue gear, so it has a much reduced speed. How do we calculate the overall gear ratio for that? Alright, so we say the two middle gears have a common axle, so they're going to rotate at the same speed. Alright, what this let us do is the final gear rotates slower and produces more torque than if it were connected directly to the driver gear. Alright, so how are we going to do the gear ratio? Alright, the gear ratio between A and B is going to be 40 divided by 10, 4. Alright, the gear ratio between C and D, alright, D's the output, C's the input, alright, is going to be 2.5, 50 divided by 20. So the gear ratio of the entire train is the gear ratio between A and B multiplied by the gear ratio between C and D. So what does that look like? 4 times 2.5 is 10. The overall gear ratio of this is 10 to 1. The ideal mechanical advantage of this gear train is 10.